any handles on what might be happening. But yeah, now that you have the massive neutrinos, what do you do with that mass? So you can treat neutrinos as any other massive particle and insert on top of the standard model left-handed neutrino and right-handed anti-neutrino, their counterparts of right-handed neutrino and left-handed anti-neutrino. However, we don't see those interacting via the weak force. So that's a little strange to have those neutrinos in order to give neutrinos mass, but not see them interacting the same way. Another strange thing is that if you look at those two, for example, you don't really know how they're different, right? So normally neutrinos or particles and antiparticles, they have the opposite charges, but in case of neutrinos, they don't have charge. And therefore, the only difference between, say, right-handed neutrino and right-handed anti-neutrinos is this antiness, which, what is that? No, there's no reason that should be different. And therefore, you can say that maybe the neutrinos and anti-neutrinos are indistinguishable. And that's what's called the Majorana neutrinos. In order to see whether neutrinos are Majorana or Dirac particles, you would want something where you can see the interaction between neutrino and anti-neutrino to see how they combine. This, knowing that neutrinos interact very, very rarely, is super difficult. So how are you going to do that? You need a large volume, which results in the only practical way to confirm that neutrinos are Majorana particles would be through the neutrinoless double beta decay. So double beta decay itself is a standard model process that has been observed in certain isotopes. Importantly for SNO+, one of them is tellurium-130, which is our choice of the double beta isotope. And in this process, you have two nucleons of the same nucleus undergoing a beta decay simultaneously. So from that, you get two neutrons converted into a proton. You have two electrons coming out of that reaction and two anti-neutrinos. Because this has to happen simultaneously, the half-life of that process is usually very long. Now, in the case of the neutrinoless double beta decay, as the name suggests, you don't get any neutrinos coming out of it, meaning that you only get the two electrons which carry the entire energy of this decay. In this case, the process is mediated by a virtual neutrino. And in order to be able to do that, as you can see here, you need the antiparticle and the particle to be the same. You also need the neutrino to be massive, because in order to conserve angular momentum, you need there to be a helicity split in here to make this possible. And throughout this seminar, I'm assuming light neutrino exchange, which is what the Stamen diagram is for. There are other ways this process can happen, all of which require Majorana neutrinos, but I won't be talking about those. So in order to look for it, this is the experimental signature. So as I said, all of the energy of this decay is carried away by two electrons, and their sum then lies around the Q value of the decay. In the dashed line, there is the two neutrino case, which has some of the energy carried away by the two anti-neutrinos. So how often can we expect this process is given by the half-life here. The two factors here are nuclear factors, the nuclear matrix element that is associated with quite a large uncertainty, and a phase space factor. And then it's also given by this effective Majorana mass, that is the weighted sum of the squares of the first row of the PNMS matrix elements. The reason why this is here in the square is again due to that helicity flip and the W boson interacting with the electron neutrino, which is why you only take this first row. So now we know quite a lot of those we've measured quite a lot of those elements. So you can plug in those numbers that we've measured, and you can create the allowed regions that where this process can lie. So on the right here is something that's colloquially referred to as lobster plot, where you have this effective Majorana mass as a function of the lightest neutrino mass, which is different in case of the inverted hierarchy and normal hierarchy. As you can see, here's plotted the current best limit coming from Canlan-10 experiment. This band on the upper limit comes from the uncertainty on the nuclear matrix element, so we actually don't know whether the limit is here or here. But what you can see is that it's starting to probe this this flat portion of the inverted hierarchy region. So obviously, we would like to do more and probe more of that allowed region. So how do you do that, and how do experiments usually approach this? So in a simplest way, your 90% confidence limit will be guided by a formula like this. So it will be proportional to the square root of the lifetime. So how long you take the data, inverse of the square root of the background. So anything in your region of interest that is not signal, the efficiency, and the number of the double beta isotope. So normally you will have something like this with the background, with your ROI, and with your irreducible 2 neutrino double beta. So you can go in various directions in terms of how you improve on it. You can mainly focus on those two things because lifetime is usually comparable between the experiments, and so is efficiency. So in terms of reducing background, there is a number of strategies. So the first one is that you just reduce the background by removing it somehow. So either purification or active rejection by some particle identification techniques. A little more subtle way to do this, which a lot of experiments employ and is really important, is improving your energy resolution. So the wider your neutrinoless double beta decay peak is, the larger your region of interest has to be, and therefore more backgrounds will leak into it. And finally, the isotope one is kind of self-explanatory. You get more isotope, you get more decays. Some of this scales this background as well. So depending if more isotopes means just that isotope with no correlated backgrounds, or if you're introducing more backgrounds in the process as well. And of course, you're scaling the 2 neutrino background in this case as well. So all of these strategies are explored by various experiments. Usually the smaller, more modular experiments have very good energy resolution, but they lack the scalability. The bigger experiments like organic liquid scintillator, which is what is currently holding the best limit on this process, usually have much poorer energy resolution, but are very scalable. And then there's caveats on how flexible you can be with your choice of isotope and what comes from that. So how do we plan to do this? What is the SNO classes strategy? So this is a schematic of the SNO class experiment. In the core, there is about 10,000 photomultiplier tubes that are mounted on this 18-meter stainless steel support structure. And they're watching this acrylic vessel that's 12 meters in diameter and its contents. The vessel is held in place by hold up and hold down ropes to prevent it from floating. And there is 7 kilotons of ultra pure water everywhere between the cavity walls and the acrylic vessel in order to shield it from radioactivity inside the QTs and the rock. Now, the inside of the acrylic vessel is what is our so-called target. So the liquid that is filling the inside of the acrylic vessel is defining what sort of phase we're in and what physics we can do. So we finished our water phase, which was 900 tons of ultra pure water in 2019. And then we started to take out the water from the bottom of the acrylic vessel and filling liquid organic scintillator from the top. And that scintillator currently doesn't have any isotope in it, which is what's called unloaded scintillator phase. And then eventually for the Neutrinoless double beta decay search, of course, we need the isotope, so we are planning to load more than 4 tons of natural tellurium for this phase. The experiment is located at SNOLAB, which is in an active mine in Creighton, in Sudbury, Canada. It provides us with very high rock overburden of over 2 kilometers, which results in about 2 to 3 muons per hour inside the snow plus detector. You can see that the lab is quite expansive. It's all based around the old snow cavity, which is where snow plus is. And you can see a picture before it was filled with the ultra pure water. The entire room is, or the entire lab is maintained as a clean room, which in terms of being in an active mine actually means quite a lot of cleanliness procedure because the mine is very dirty. On top of traveling 2 kilometers vertically, you also need to travel 2 kilometers horizontally, which sometimes is through mud and wind and dust. And so everybody has to not only change from their mine gear into clean room clothes, but also shower completely, and every equipment piece has to be cleaned. All of these wires and tubing has to be unspooled. It's joy.
Different experience.
Yes. No, it's very exciting. Very good. So with this setup, what that can give us and what are the highlights of what we're doing? So I said 12 meters in diameter, 4 tons of tellurium, 1 kiloton of liquid scintillator. We are a large volume, high exposure experiment. We are using tellurium 130 because it has a high natural abundance of 34%, which again translates into a high exposure. We have underground purification and storage, which mitigates our backgrounds. We are planning to do an isotope, or we are currently performing an isotope out measurement, which constrains our backgrounds that come into the ROI and therefore allows us to have a good measure of it before the isotopes come in. And I will talk a little bit about our particle identification as well. So here you can see how our region of interest is expected to look like in the reconstructed energy. Here in the Monte Carlo, we also put in a fake signal of Neutrinoless double beta decay with effective Majorana mass of 100 millielectron volts. So that's how it would look like for us. This is just taking that and putting it into a pie chart of what is our background budget. So you can see the boron neutrinos from the sun are the most dominant backgrounds. And then you have some internal radioactivity. You have radioactivity coming from the outside of the acrylic vessel. You have some alpha N reactions that are reducible to neutrinos, beta-beta spectrum, and some cosmogenics, again, which I will talk about in a little bit, but forming a small portion of this. So just as a preview, before I get more into it, where does that put us in terms of the scale of Neutrinoless double beta decay experiments? So if we loaded the 4 tons translated to 0.5% tellurium, we expect about 2 to the times 10 to the 26 years after 3 years of data taking. And that's kind of put into context here. In this plot, it's showing the effect of Majorana mass as a function of the phase space weighted half-life. It's plotted this way because here everything on the x-axis is not model dependent. So the phase space varies for each element, but it's not model dependent. And if you're comparing between different experiments using different isotopes, you can either use the half-life, which is not really indicative of the effective Majorana mass, but then the effective Majorana mass includes these nuclear elements that really depend on the model. So plotting it this way, you can kind of see the spread for each isotope and where it is. And so what we're looking at here, the blue solid line is the current best limit from Hamlet-Venn, and in red is our projection for the 0.5 tellurium. And you can see that we're starting to probe the inverted hierarchy as well, but we're hopefully be loading more tellurium and taking data for a little longer. So coming back to where we are and what are the phases into the experiment, and I will also want to share some recent news that we're quite excited about, some recent papers, or paper that we published. We're filling in stages. I explained that there's first water, then there's liquid organic scintillator, and then there's tellurium. All of these stages, apart from doing different physics and us being multi-purpose neutrino detector, also allows for characterization of the detector and the background. So the water phase, which finished in July 2019, allows us to measure the external background. So the background is coming from the acrylic itself, from the water shielding, and from the PMTs. This is much easier to do in water because it's a studied medium, but also because you get a directionality. And so you know that all of the external backgrounds that are coming inside the acrylic vessel are coming indeed from the inside, because you get these lovely Cherenkov rings. And this is our event display during this phase. And also calibrating the optical response of the detector is easier if you have a medium that has been measured previously. So that has also been completed in the water phase. We've published papers on solar neutrinos and invisible nuclear decay, but also very recently on reactor antineutrinos in water. So you can use neutrino detectors to detect reactor antineutrinos. In our case, in SNOLAB, there are 3 in a vicinity of SNOPLUS experiment, and you can get this process where the antineutrino reacts in inverse beta decay, giving a prompt response from this positron, as well as a neutron which then thermalizes, captures on a hydrogen in terms of in case of water, and produces 2.2 MeV gamma as a delay response. Now, in water, this has never been done, mainly because this 2.2 MeV gamma is very low energy, and the Cherenkov detectors usually don't have the trigger threshold that is capable to do that, and there is a lot of backgrounds in that region. However, for SNOPLUS in water phase, we've achieved very low backgrounds, and our detector threshold was only of 1.4 MeV, and therefore we observed antineutrinos from the reactors in pure water. And you can see the plot from that paper here. And so this generated quite a lot of interest, and we are excited about it. It is a demonstration for us of how low our backgrounds are, how good our threshold is performing, and that's interesting for the neutrino community. It's also interesting from the perspective of non-proliferation and detecting reactors in water, which is much cheaper than something that is doped or that is oil. Okay, moving on. So removing water, putting scintillator in, pandemic happens. So we also got this partial scintillator fill phase in which you can see on this picture that you have an interface between the water on the bottom and the scintillator on the top. So that is a 2 media detector that we were stuck in for multiple months. However, we adjusted our reconstruction algorithms, and we were able to perform not only measurements of reactor neutrinos, but also demonstrated some directionality in scintillator with this particular scintillator mixture we had at that time, and also already made a big progress and jump in measuring our backgrounds. So the scintillator itself is linear alkyl benzene, and I'm not going to go too much into the chemistry, but we also use two fluors with it. Currently, we have this BPO, and we're waiting for business B to be present. But importantly, we have underground scintillator purification plant, which we can keep using to purify any scintillator coming in. So at the moment, this is where we are. We have all of our primary fluor in, and we are performing our isotope out measurement. Again, we're also doing some supernova reactor and neutrinos at that same time, and I'll talk about what is the result of the backgrounds and how does that compare to what I've been advertising at the start in a little bit. And then finally, we're expecting to start taking tellurium data in 2025 with first 0.5% tellurium loading by weight, but already being confirmed for 3% in the future. So why tellurium and how do we get tellurium in? So tellurium is a great double beta isotope, primarily because of its very high natural abundance of 34%. It also has decently large Q value of 2.5 MeV and a decently long 2 neutrino beta beta half-life. So the problem with this is that you very often have tellurium in inorganic compounds, but we would really want to load this into an organic scintillator. So for that, we start with telluric acid, which has those 6 OH groups, and we perform a condensation reaction, which in kind of short terms just wraps it in some way with those nice and lovely organic tails. And we've published this loading method, and we've had samples that have been stable for a very long time. Very important point to make here is that as we load more tellurium, we need to make sure that the light yield of the scintillator stays high. So currently for 0.5%, we still have almost 500 PMC hits per MeV at Snow Plus. So this is what I will be showing all of the predictions with. That is with this loading method that we've developed. All of the purification of the tellurium will be done underground in this telluric acid purification plant. And all of the chemistry from the previous slide will be done in a different tellurium butanediol synthesis plant. So both of these plants exist as NOLA, and they're being commissioned. After the purification, we expect the order of 10 to the minus 15, so 16 grams per gram in the uranium and thorium chains. Okay, so what do we expect for the neutrinos double beta decay search, and in more detail, how do we plan to achieve this? So bringing this slide back, this is our background budget and how certain we are that this pie chart that I showed at the start is actually trustworthy. So let's take them one by one. So in terms of the internal uranium chain, we have various methods of mitigation. So firstly, the scintillator purification plant that I mentioned. Secondly, there is cover glass over the top of the acrylic vessel, which prevents any new ingress of internal radioactivity. Then we are pretty lucky in terms of where our region of interest is. There are coincidence decays where the daughter of the isotope that we would be worried about decays pretty fast, and therefore you can use coincidence tagging to remove that. And not only you can remove it, you can also measure it using this coincidence tagging. So that is what is shown here is the measurement of the uranium chain based on using this tagged BIPO sample. And this is where we get the prediction from our scintillator to be 10 to the minus 17 gram per gram for both of these chains. For the external backgrounds, which is mainly the gammas penetrating inside to the scintillator volume. The first line of defense is mitigation by cutting part of that volume and creating your fiducial volume where you're creating your analysis. You can also, again, measure this, and this is from a water paper on nuclear decay search from our water phase. Again, as I mentioned, it is much easier to measure it there, and we have our constraints on our external backgrounds, and they're all on target and as we expect. Finally, we can also do gamma beta pulse shape discrimination to some extent in the current scintillator and the tellurium loaded scintillator, as it's shown on here, where in blue it's thallium-208 events from the acrylic vessel itself, and how that can be rejected as a function of the signal. And I will talk about this method in a second. So then finally, in the other reducible backgrounds is the cosmogenic backgrounds. So this is decay of isotopes that are created from spallation on the tellurium itself. So now this is the one background that we can't measure before we have the isotope in. We can measure it externally, but it's not the same tellurium. It's really important to measure this once it's in the acrylic vessel. And there's a number of those isotopes that can be created by the spallation. And in order to reduce them, we purify the isotope that we're loading, the telluric acid, and we store it underground so that a lot of these isotopes have time to decay away. So a lot of these are their half-lives is around a few years. So this tellurium has been underground since 2015, and therefore by the time that we're purifying it, again, we will have very small contamination by these cosmogenic backgrounds. Nevertheless, if you look at this energy spectrum and notice that the black line is the Neutrinoless double beta decay peak in simulation, you notice that a lot of them overlap. But in particular, there's this cobalt-60 peak that looks almost exactly as the signal. So if you look at this and look at the reconstructed energy, you have to ask, how are we ever going to measure Neutrinoless double beta decay? So important to notice, again, this is normalized count. This is just looking at the shape. We don't expect these backgrounds to be this high. But also, even if we don't expect them that high, if we made a discovery, we need to make sure that we can convince people that this is not just cobalt-60. And this is where pulse shape discrimination becomes even more important than for the external gammas. So how do we do this pulse shape discrimination? At SNO+, we reconstruct everything using just the PMT information. So each PMT has its position and it has the time that it has been hit. We then take a spectrum that's called the time residual, which is basically just the time of the hit corrected by the time of the flight, which should give you basically the scintillation profile. You can then do a likelihood fit, and from that figure out the time and the position of the event. Our energy resolution is about 10 to 15 centimeters, and we reconstruct everything under the hypothesis of an electron, so of a point-like particle. The electrons normally travel less than a centimeter, so our energy resolution is really greater than that, and they are really truly point-like. However, if you have even one MeV gamma, that travels a little further, and so your energy deposition will be more spread out. And therefore, if you're doing something like a likelihood fit, those time residuals will appear more spread out. You can take that, create PDFs, and you can create a discriminator, something like a log likelihood ratio. So that is what is shown here. This is our Monte Carlo prediction for the tellurium phase and the performance of such discriminator. So Neutrinoless double beta decay in red, and then the worried cobalt-60 in green and external background in blue. So you can see that you can probably use this to cut out some of the background, but you can't do event by event discrimination. So good, but you can also use this later in a bit, and I will show what does that mean. Okay, so I said we did already some isotope out measurements, and this is an analysis done in the partial fill phase. So that complements to all of the measurements that I've said we've already done, and they're all in agreement. And that's denoted by these sticks here of, okay, we understand the internal backgrounds, we understand the external backgrounds. We, well, understand the two neutrinos beta background because we know what the half-life is. That has been measured. There's nothing going to be changing on that. And of course, we know the flux of the solar neutrinos. So really, we are in a pretty good shape to trust this pie chart in terms of our predictions. So you can just translate it as the prediction that I've given you for the counting analysis using the simple formula, but you can also do better by feeding this into something like a likelihood analysis. So what we do is we perform a multi-dimensional Markov chain Monte Carlo analysis, which is based in, of course, reconstructed energy, but now you can extend the ROI a little bit further, which helps you constrain some of the sidebands of the additional backgrounds. You also can do it in radius, which helps further to essentially remove the external backgrounds and break the correlation with the external backgrounds. And you can use also the value of the log likelihood or any PDS classifier that you've developed as an additional dimension in this fit. So this is one of the bins in the volume corrected radius and how that fit performs in Monte Carlo. And you can see that the result of that fit is basically what you get from the counting analysis, but you get it in 3 years instead of 5. So you get some gain in the half-life, but where this is really powerful is actually when you start looking for discovery potential. So yes, you effectively decrease some backgrounds by using this and increase the limit, but when you're looking for discovery, you really need to make sure that nothing is correlated with your signal. And that is exactly what the PDS dimension is doing in terms of the cobalt-60 and the cosmogenics, because those are floated in the fit as well. So in this case, on the plot, I'm showing how well do you do in terms of the effective Majorana mass with and without the pulse shape discrimination. And you can see that it helps to restrict or to discover effective Majorana masses that are 40 to 50% lower. Importantly, it also answers this question of if you saw a signal, how can you ever trust it? So in this case, we inject our sample with some crazy contamination of cobalt-60, right? So we've seen or we've confirmed that the cobalt-60 is our most correlated background, and then we've put it into our simulation data set. Important thing, this is blown out of proportion compared to what we expect, again, the actual contamination of cobalt-60 to be, but it's blown out to be proportional to high effective Majorana masses. And the fit returns 0 Neutrinoless double beta decay counts in all of these cases, apart from the case when you've actually injected the draw signal. So this is really important in showing you that if we would see a bump, it would indeed be a Neutrinoless double beta decay discovery rather than some contamination of an cosmogenic. So what is the outlook for the future? So first of all, I mentioned that we can load with higher percentages of tellurium, and that is guided by how much light you lose as you load more tellurium. So as we are getting better in our loading technique and developing new methods and potentially doing the synthesis using a new additive, this dodecyl I mean, we see that those loading methods have different rates of decay of the light yield for the given percentage of tellurium loading. So we already are planning to do 1.5 and 3% tellurium, and you can imagine that especially the 30% will really allow us to go deep into the inverted hierarchy. Okay, what do you do next though? Say you probe the inverted hierarchy, but you want to go further or much beyond that. So the current proposal of the Theia detector is in the works, and there's multiple R&D efforts that could be incorporated in this big liquid scintillator detector. So liquid scintillator R&D is one of them. A lot of people are looking at whether you can use water-based liquid scintillator that would have the advantage of the directionality of Cherenkov detector, where you can, for example, discriminate of something like the boron-8 neutrinos, right? That is our most dominant background, so we really want to remove that. Another way you can distinguish between Cherenkov and scintillator light could be those devices called dichroicals, which basically have long pass and short pass filters that direct the light of different wavelengths into different photosensors, and therefore you can basically do spectral sorting and have predominantly light from Cherenkov and scintillation in different detectors. And of course, other high quantum efficiency PNTs or fast PNTs are also an option for a high loading detector like that can go further. So yes, significant R&D efforts ongoing on multiple fronts. There is a number of smaller scale demonstrators for Theia that look at different approaches and different parts of this R&D project. I list some of them here, and the one that I work on and want to particularly mention is EOS demonstrator that's being built in Berkeley. It is a 4-ton acrylic vessel, and it has dichroicals at the bottom. It uses water-based liquid scintillator, and it also uses different photomultiplier tubes and a directional source. So we're planning to demonstrate the directionality in this scintillator based detector. And we're currently in the phase of building the detector, and we're planning to start taking data around 2024 next year. So that's all I have. So I would like to thank all of these people who helped me put this together, and I've shown a lot of their work. This is from our collaboration meeting in the summer, which was the first collaboration meeting since Stola started taking data that wasn't at Stola. We decided to be very exotic and go to Kingston in Ontario, so southern Ontario. But yeah, you see everybody's happy about that. So thank you very much for listening and coming and your attention.
Okay, yeah, thanks for a great talk. We have some time for questions. So first of all, I'm going to see if anyone on Zoom wants to ask a question. Okay, it doesn't look like it. So yeah, maybe open the floor to people. Yeah.
So thanks for the really nice talk. So you looked at cobalt-61. I mean, are there other unknown spallation products in the table of isotopes that could play a role even if one of the cross section?
Yeah, so I mean, there's a really rigorous paper by Valentina Loza, who looked literally at anything that could be produced on tellurium-130. And the kind of spectral plot that I showed has about half of them only. And so out of these, we've looked at anything that has a count higher than 1 per year, and check the correlate higher than 1 and doesn't have like an additional peak, for example, like the cobalt 58. But yeah, I mean, there could be, right? There can always be more stuff. But yeah, the selection of cobalt 60 here is really by looking at the correlation in the fits themselves and selecting that one as the most correlated. Yeah.
Yeah, that's my question. So I'm assuming these are backgrounds from when the tellurium was above ground and still, cooling down, and these are the products, or is it muons, cosmogenic muons coming into the detector itself and getting it?
No, so this is from when it was on surface.
Oh, I see.
Yes.
Okay.
Yeah. So you're right, there will be some equilibrium feeding of those isotopes just from, we still get those 63 muons per day.
Right.
But
So you're not worried about those?
no, not really. Yeah.
Just to tag on that, how does the tellurium actually like ship to the site? Is it like by plane or?
Oh, I have no idea where we bought the tellurium from. But yeah, I'm assuming our liquid scintillator just arrived there on like in tanks.
Really?
I'm assuming this is pretty much similar. Those are, those drums. The last portion of the journey, everything has to go on the cage that people go on. So actually getting the like acrylic vessel, you have to do it in pieces. I mean, that's what's noted. We didn't have to deal with that, luckily. But yeah, everything has to go on like a small cage, which brings it underground. But yeah, at the moment, this is a powder, so it can be packaged in drums.
I also had a question about the cobalt 60. So if I remember nuclear physics right, it beta decays, right? So how does the, I guess, signal of the beta decay of cobalt look different enough from the neutrinoless double beta decay signal that you can discriminate between the two?
Yeah.
Like in terms of like the timing of the electrons moving.
Yeah. So this is, I don't know where I put that line across here, but you have this last gamma. So this is the decay spectrum of, so it does beta decay, but you have additional gammas. So the name of the game in the false shape discrimination is not that it's not a beta decay, but that you have those additional gammas that also happen, and those travel far further. This last gamma that you basically get almost 100% of times is like 1.3 MeV. So that's the gamma that you or discriminate on.
So I have a question on slide 44. You showed a graph. I think you showed it right at the start of the presentation as well. So yeah, on this graph on the left, what exactly does it mean to go into the like inverted hierarchy mass scale for this?
Yeah, so maybe I can go to this plot.
Yeah, okay.
Yeah, so I know it's kind of just zoomed in on the inverted hierarchy region, and indeed, even if you're not you're still probing this degenerate region, even if experiments say you're not even getting sensitivity to inverted hierarchy, but you are in this region.
Okay.
There's also limits from cosmology that start cutting into
Sure.
there, but yeah, it means that you are in a region where you could expect neutrinos double beta decay.
Okay.
Because, for example, so here we know it's not gonna.
Okay, cool.
Yeah, I guess same slide. Sorry, slide 44. Did you make the plot on the left?
I did not.
Okay, do you know why like Nexo and Cupid are not there?
Right, so it's I know this. Yeah, so I believe we have multiple versions of this plot. I like the version which only has predictions for snow plus. So it has so all of the solid lines are published results, right? And then the projections are in dashed or dotted. I don't know why this one has legend 200 and Kamlanden on it, but
Do you know where Nexo and Cupid rely on that plot? Or people from Nexo and Cupid?
Yeah, maybe I'll say this is like a shockingly controversial topic, as many people know. I think there was a lot of work in the kind of long-range frame town hall to get that all collaborations group to do the columns in the white paper. It does look a little different than this. We can find this possibly, but
Okay.
it's, you know. It's gonna be, you know, the non-intensity part of this property is really just selling it, so it may be moving further to the left, or to the community.
Okay.
Version.
Okay, well, if there are no more questions, then let's thank Tereza.